let's now hear from Steve Cerwin. Steve is a retired research scientist from Southwest Research Institute, and he is a guru of interpreting HF Doppler shift observations and what it actually means when we see it, what it actually means relative to the ionosphere. So Steve, take it away.
Okay, let me see if I can get this going here. Is that showing up?
It sure is.
Excellent. Okay, I'm going to talk to you about, we've seen a lot of Doppler shifts and trying to back calculate what the change in the ionospheric refraction layers be to produce that Doppler shift. So we've taken a lot of data sets that, let me see if I can get rid of that. There we go, it's better. We've got spectrograms from the Doppler frequencies, ionosonde data, time of flight measurements, and ray trace simulations have been acquired for a bunch of different days and frequencies and events. And this is kind of a mesh trying to make sense of all those things together. Recently, we've been trying to calculate the change in refraction layer height that you get from observing the Doppler data. And notice that it is a change in height because Doppler tells you a rate of change. And then correlate these data sets in some sort of a combined attempt to understand certain elements anyway of Doppler shifts and mode splitting that we see. And most of the data that I'm going to show you here is Colorado, WWV down to Texas, under San Antonio, that kind of a path. So 3 particular experiments are some positive Doppler shifts and mode splitting that happened during the morning of the Festival of Frequency Measurements in October of 2019. Data acquired by WA9VNJ that gave bipolar frequency swings during the Eclipse of 2017, and correlating the models with the time of flight measurements taking back in 2020. Well, let's go. There we go. So here's a simulation provided by Carl Lutzelswab, K9LA, that shows what kinds of things can happen during a morning transition. You see it's a busy time. You can have single or multiple hops from the F layer. You can have single or multiple hops from the E layer. You can have these Pedersen rays, and this changes dynamically with time. Now, the reason we see Doppler shifts, Doppler always implies a change in path length. Well, the transmit and receive sites are fixed, so what's changing? Well, it's the reflection off the layer height. The layer is changing. In the morning, it lowers, as John said. So here's a simple geometric model that relates what the path length is, and path length is what changes in path length is what causes Doppler. So you have to use some sort of a geometric model to relate path lengths to altitude, to the height of the layer. And so here's a simple model showing 1 hop, 2 hop, and 3 hops. Obviously, with the endpoints fixed, the more hops you make, the longer the path is. So if you have these multiple simultaneous modes, 1 hop, 2 hop, 3 hop, the more hops traverse a longer distance, so that when the common layer height lowers, those longer paths have to have more absolute change in the same amount of time, which means they're moving faster. That means you get different Doppler shifts for 1 hop, more for 2 hop, and more still for 3 hop. So these are, here's some data on that Festival of Frequency Measurements day from Fort Collins, Colorado to down near San Antonio. This was done at 5 megahertz. And importantly, I did not have my GPS DO available for this data set, and you're going to see what effect that had. So here's the spectrogram taken during the morning. This starts at the pre-dawn hours in the middle of the night down here. There was a pre-dawn traveling ionospheric disturbance pointed out by Nathaniel. Notice that the entire event is below the 0 frequency line, which we'll see what that does to the data in a minute. Dawn starts right around here. Here's the positive Doppler shift. And we believe that is 1 hop off the F layer. This line down here that doesn't move hardly at all is hypothesized to be from the E layer, which shows very little change during the day. And then finally, this mode splitting, this higher order mode here, is going to be calculated as 2 hops using that model I showed you previously. So this data was digitized so that I could feed it into Excel to work on it. Here's the 1-hop mode, and here's the 2-hop mode. So these are the 2 pieces of data I'm going to use to back project what the layer height had to do. So here's the result. The process is you take that Doppler frequency data and you convert it to path velocity. And that's a function of frequency. For example, at 5 megahertz, you multiply the Doppler shift by -60 to turn it into meters per second. 10 megahertz, it's only 30, so it's frequency dependent. So once you get path velocity, you have to calculate the change in path length, and you do that by doing a cumulative sum integration on the velocity profile. See, the Doppler comes from the derivative of height change. That's what we're measuring. So to get back to that height change, we have to do the inverse operation or integration. So we can do the backwards integration, cumulative sum process on the velocity curve to get the change in path length. And then you have to use that model to convert the path length changes back to layer height. And that's where this curve came from. Now, all integration processes, have that plus C on the end of it, which means you lose absolute reference. The Doppler calculation only gives you change, relative change. If you want to pin it down to an absolute height, you have to get a starting point from someplace else. This was taken from an IRI far-lap simulation, 300-kilometer start height. You can also get it from an ionosonde if you've got one handy. We're going to talk about that more and how perfect the tangerine would be for doing these kinds of measurements. Of importance on this graph is that this blue line was calculated from the Doppler track that we identified as 1 hop, and this other one was identified from 2 hops, and they agree fairly closely, which means that the model has some verification. So here is data from an ionosonde at Boulder. Now, Boulder is completely north of this entire path, and it's some 750 kilometers away from the apogee between Colorado and Texas, but nonetheless, it's the only real ground truth data I have. This is for an entire day. So here's the morning transition right here, where the layer height decreases. Now I'm going to overlay on here the layer height calculated from the Doppler shifts from the previous page. Remember that traveling ionospheric disturbance? It was all below the 0 frequency line that caused this positive shift over here. But then the timing of the layer decrease during the dawn transition lines up pretty doggone good. I took that graph and matched up the scale. See, here's 300 kilometers, 300 kilometers. Here's 200, here's 200 of the F layer. Timing came up just right, but the amplitude down here is off quite a bit. This doesn't flatten out till about 35 kilometers below ground truth. So why was it off that far? Answer is, I didn't have a GPS DO. So there's been a lot of talk about how important this part in 10 to the -9th is. And here's what happens to you if you don't have that. A frequency error is the same as a constant velocity offset in the layer height. And if you're integrating over a long period, like this is a 5-hour period from 10 Zulu to 15 Zulu, that error can integrate up to a big number by the time you get to the end. So these 5 curves here, I went back and took my data and added a 10 millihertz offset. So here's what that data would look like if I was off 20 millihertz, 10 millihertz on the negative side. Here's what I actually measured by calibrating with WWV. And then here it is with positive changes. So the point is that a 0.04 hertz range and frequency uncertainty gives you a height spread of 80 kilometers over this 5-hour path. Now what I did, since I didn't have a GPS DO, I picked the quiet daytime E-layer return of WWV on 5 megahertz and used that to calibrate my receiver. But it was off. How much was it off? It looks like it was off by about 15 millihertz. 15 millihertz is all it would take to make that calculated plot lay right on top of the Ionosonde data. So yes, you do need a GPS on both ends, and these are the bad things that can happen to you. Now, I will tell you, what does it take to hit the green box on an ARRL frequency measuring test? A hertz, 1 hertz. 15 millihertz will get you in the green box every time, but it won't do for these kinds of measurements. Okay, so here I'm going to move to the Eclipse. This was done at 10 megahertz. This data was acquired by WA9VNJ. The path here was from Fort Collins, Colorado to near Milwaukee, Wisconsin, and it was done at 10 megahertz. So here's a setup. The Eclipse path of totality followed here. Here's WWV Fort Collins. Here's the receive side over here. And you can see that the Eclipse actually transected the propagation path. Here's where the ionosondes were. Here again is the propagation path. Here comes the Eclipse path crossing it. The Boulder ionosonde is the nearest one that we could get. So here's his data. You can see the, as John talked about, the gentle all day long from high to low, gentle change in Doppler frequency on 10 megahertz. That characteristic at 10 megahertz has been observed numerous times. John showed you one, here's another. And here's the effect of the eclipse, this negative first, then positive S-shaped curve. It went negative because as the eclipse blocked out the illumination, the layer height rose, got higher, which made the path length get longer, which gave you a negative Doppler shift. And then it stopped moving in that direction, started coming back down as the illumination from the sun returned, and then that gave you the positive Doppler shift as that path lowered. So same trick, convert this Doppler frequency to path velocity, this time using 10 megahertz instead of 5. Use that to calculate the change in path length through this cumulative sum integration process on the velocity profile, and then finally convert that path length change to layer height change using that geometric model. So this amount of Doppler shift relates to this amount of height change. Remember, it's only relative. You want to put this in absolute terms, you have to pick some starting height from something else. So it looks like the eclipse caused about a 65 or so kilometer change in layer height. Christina Collins compiled this overlay of Boulder ionosonde data. This is the actual layer height as a function of time of day. So here's 0 Zulu over here. Here's noon UTC, which is about when the eclipse happened. Actually, it was closer over here to 17 Zulu. And then here's the next day. 2 days are here, the day before the eclipse and the day after. The blue one is the day before the eclipse. That would be like a normal day. And then on the day of the eclipse, what's different? We got this bump here where the layer height went up as the shadow of the eclipse crossed the propagation path. If I overlay that calculated data, it fits on here like this. Now, at this time, a GPS DO was used, so the amplitude data came out spot on. So this back projecting height change with a measured height change from the Boulder ionosonde came out pretty good as far as duration and amplitude, pegged it very, very closely. These scales are matched up. Here's a 100-kilometer range here. Here's a 100-kilometer range here. And then these time increments exactly match these down here, but offset a little bit. Differences, a little something funny happened over here that wasn't accounted for by the Doppler data. And the times don't exactly line up. For example, here's 17 Zulu here, here's 17 Zulu here. Why is that? Well, probably because the Boulder ionosonde was completely west of this path, and it was west by some 750 kilometers from the apogee, where this was actually interacting with the F layer. But still, that's encouraging data that it matched up as well as it did. Finally, I'm gonna weave into here some time of flight measurements that were taken back in 2020, because it helped show that the model, that geometric model that we're using actually does make some sense. So this is back from Fort Collins down to Texas at 5 megahertz. So here again is the model. And again, as this layer height changes for all 3 of these, it changes the path lengths of all of them. Here's the relationship over here between what the path length actually is once you define the endpoints and how long the ground path is. Here's for 1 hop, here's for 2 hops, and here's for 3 hops. So as you vary h, what happens to the path length? That's what this chart on the right shows you. Here's reflection height that goes from 100 to 400 kilometers. Here's the time of flight for a 1-hop mode, time of flight for 2 hops, time of flight for 3 hops. So the total path length does increase with number of hops. You notice that the slopes change. Slope is steeper for 3 hops than it is for 2 than it is for 1. And this ties in nicely with the previous observation that the longer paths have to shorten faster because they're longer. The endpoints are fixed, the height is changing, the longer paths shorten in the same amount of time as the shorter paths, which means that the longer paths have more velocity. And that velocity change is reflected by the slope of these curves. So during that experiment back then, we measured a bunch of time of flights. We used the timing tick of WWV. That's 5 cycles of a 1 kilohertz tone. That's what you hear every second on WWV. You can get a 0 reference from the leading edge of the 1 PPS output of a GPSDO. Use that as a scope sync. Use a particular point on the cycle that you received the timing tick from, and you can get time of flight. So I measured a bunch of these over the entire morning transition, plotted them, and they clustered in these linear fashions, which correlate really pretty well with the layer heights and that model. So if I wanted to see how well these correlate and at what height do they correlate, I have to do just a couple of things. You notice that this data was taken as a function of time. Here's 12 Zulu, here's 1530 Zulu. And this was during the morning. So the layer height was decreasing. So the time of flights were getting smaller. So all of these graphs are high going low because the layer height was lowering. This graph calculated time of flight versus layer height. So this is an ascending graph down here. So the first thing I got to do to overlay these to see if they match up is flip the cents, and then I have to do the scaling to find out where it fits best. So there is this data flipped so that they go in the same direction, and then adjusted in amplitude and width so that these match up as best they can with the calculated values. And you can find a spot where they match up pretty well. And that happens at around 250 kilometers height, which is right in F layer region. So here's another way to tie in layer height, but this time from time of flight. And this also tends to support that multi-hop model, as simple as it was, that was used for the previous Doppler-to-Height calculations using frequency shifts. And then finally, to get yet another ground truth point, compared the time of flight measurements for the 1-hop mode with that predicted from a simulation using an IRI monthly average ionosonde. And I can overlay these as well, and they fit pretty good. Don't know what happened here around 13 Zulu. It's real. There's more than one data point down here, but for some reason, the time of flights took a little nosedive, but outside of that, they line up pretty well. So the model seems to make sense, and it does support the 1 hop, 2 hop, 3 hop divergence that we see in the Doppler data. So we've kind of seen that Doppler ships over a given path. They come from the time derivative of changes in ionization layer height. So you can get that height change deduced by an inverse integration process on the measured Doppler data. We've got layer height profiles calculated from measured Doppler data, and this compares pretty well with Ionosonde data and some of the IRI simulations. So these initial tests are pretty encouraging. Combining the calculated data with ray trace modeling and that geometric model showed results that are pretty consistent with the premise that some aspects of the observed mode splitting can be attributed to the simultaneous multiple hop modes. Time of flight measurements kind of agreed with this. In a number of these experiments, we've seen that these Doppler-produced height changes and other frequency turbulence effects occur at the F layer, not in the E layer. The signals that we've seen that we believe coming from the E layer by comparison are relatively very, very stable in the face of changes in solar input. Even eclipses don't seem to bother them very much. Signals that are believed coming from the E layer show very, very stability. And by the way, if you just do geometry analysis, it bears this out. The E layer is lower. So if you look at how fast the path changes versus how fast the height changes, it's a whole lot less than if the height were much higher. Do some simple Pythagorean theorem right triangles, and you'll see that happen. We need more data under different conditions to help untangle multiple processes. I think we can say that some of the mode splitting we've seen come from simultaneous 1, 2, and 3 hop modes, but other modes are possible. You know, it could be that rays bounce in between layers. That's known to happen. It goes up, hits the F layer, comes down to the E layer, goes back up to the F layer. That's yet another time of flight. So you need to take look at this thing from more different angles to find out what's really going on. And you really need a method that could separate the data in these multiple modes. A specific experiment to correlate Doppler inferred height change with ionosonde measurements is proposed. And man, that tangerine would be just fit like a glove for this. The experiment will use GPS-DO stabilized transmitter and receiver, absolute requirement, and you symmetrically dispose these on either side of an ionosonde. The idea is to put the apogee of the Skywave path directly over the ionosonde. So now you take data during the morning and evening transitions. These happen every day. A bonus would be an eclipse. Point is that you can, by looking at the Doppler shift on the oblique path, you can get these calculated changes in layer height, but because that apogee is right over an ionosonde, you can directly compare the two to get ground truth. The tangerine with GPS-DOs on both ends would be a natural. So either you find a couple of hams on either side of an existing ionosonde. I'm looking into using one. The Austin ionosonde is about 90 miles north of here. But 90 miles on the other side is Texas A&M University. I've contacted those folks to see if we could set up some sort of an experiment. If you could make your own mobile ionosonde, you could go anywhere you want to. These tangerines you could put into a vehicle and set these up over different paths and in different directions. That would be pretty cool. But a very significant enhancement, besides just measuring Doppler, would be to add timing markers to the transmitted signal so that you could do time of flight measurements as well. Now, the time of flights measurements I did before used those time ticks from WWV. Those are in the time domain. It was problematic because the length of that pulse is 5 milliseconds, And the difference in arrival times between 1-hop, 2-hop, 3-hop modes is less than that, which means that the returns come down on top of each other and they superimpose. So now you got to untangle and separate those in a superposition in the time domain. If we did a chirp, a tonal chirp, and do a chirp radar approach, now you spread those multiple returns out in frequency, and you can examine them each separately, and you get them all at the same time. Phil suggested a phase
1 minute
sequence. We're done. A phase sequence, and that may offer some advantages as well. But the point is that you need to be able to see these multiple returns that happen from simultaneous propagation modes of 1-hop, 2-hop, 3-hop, Pedersen, in between layers, whatever all is going on. Separate those out, get data on all of them at the same time. So that would be some cool experiments, and we're kind of looking to that to the future. Okay, wow. We'd be glad to take questions.
Thank you very much, Steve. I would like to point out, so first of all, it's an amazing presentation, getting lots of great comments in the chat. I'd also like to point out that we are on break now, so we're on break for the next 12 minutes. But we can continue to keep the webinar open during the break, and you can continue answering questions during the break, or we can have additional conversation. So thank you. Let's see. Gareth, any questions for Steve?
I am looking, and there was a lot of chit chat during the Steve's talk there, so I don't see any unless somebody does.
There's one that just got posted by Flavio Arcangelo. Despite the height change of E layer in diurnal transition, did you notice sporadic E in your measurements, perhaps with higher Doppler shifts?
No, and I think it was just a matter of luck of the draw. Didn't have any of those float by at the time. And in fact, the E layer data I have came from one of Christina's IRI simulations. That simulation was during an eclipse was problematic because it thought the F layer disappeared, which it most certainly did not, but it did show what effect the eclipse had on the E layer. And it wasn't much. It was like 15 or 20 kilometers out of 100 kilometers. Whereas the changes in the F layer are much larger, absolute and percentage wise. But no, we didn't happen to see any sporadic E contributions.
Actually, I had a question for Steve. Going back to the Eclipse data, did you notice any TIDs in the vicinity? This is just a curiosity. It's because there was a lot of
no, not during the eclipse, but I think we've got one here during the festival of frequency measurements, and that actually turned out to make this data set far more complicated than it really needed to be. But all I had for the eclipse data on Doppler was the stuff that came from WA9VNJ, which was, where did it go? This data. Actually, you know, there was something different. There are actually 3 data sets in here. There's the gentle all day long from high to low that John mentioned. There's the effect of the eclipse, which is right here, that I used to back project the change in layer height. And then if you look really close, there's a little backwards going, positive first, then negative, smaller S curve that happens right in the middle of the data set. And because
there was a flare during the eclipse too, I seem to remember. I can't remember the timing of it. Somebody.
You're right, and that's what we think it is. And if you think about the effects of a flare, the polarity, the sense of this S curve is correct. The flare sends a slug of ionizing effects into the ionosphere, so the layer initially lowers, which causes a positive Doppler shift. And there it is, sure enough. And then it quits lowering and the Doppler goes through 0. Essentially, you're following the derivative of that change in ionization. And then the layer goes back up again, giving you the back half of the negative swing. So I agree with you. I think that was more than likely a flare, but man, you talk about timing.
Yeah,
Yeah.
I remember looking at that data set and I did find a flare right at that time. So it matches up very well.
Steve, this is Phil. We should also remember, just tell people to remember that, you're measuring change in path length, right? Which can be interpreted as a change in the layer height, or if the layer stays, let's just take the other case, the layer stays in one place, but the bottom side of the layer starts to erode from whatever reason. Your reflection point could appear to go up, your path length could change. So in reality, there's some mix of both of those, I suppose, in a case where you've got, say, the sun turning off. It could be dominated by one or the other, but it's just, there have been some other papers about that. So your analysis is really showing us that there's a lot of information in here, and by doing a lot of cases, I think we can separate out some of those influences.
You're absolutely right, Phil, and I think what that reflects mainly is the crudeness of this model. This model is too simple. The simple up and down bounce off of a particular layer height is not reality. As you said, the physics of the layer height is far more complex.
Yeah,
as a first cut indication, okay.
Oh, absolutely, absolutely. And for example, like Mike in the chat just mentions that you get a flare going off. Well, a flare is going to illuminate, for example, the D region, which itself might artificially kind of change the delay, which you could misinterpret as a change in path length. So, there are these various things that can happen. The difference between that layer shape changing and the height changing has been seen, for example, by Dartmouth in doing some AM carrier measurements way down in about the megahertz range, where D region is more important and much more of a factor. But, if you just write down the equation, there are several terms in there. And so the fascinating thing is to figure out when what term dominates. And this is where modeling and data together can make a really big difference.
Yeah, excellent point, Phil.
Yeah, no, I mean, I think that's why it's important for you to, get these results out there, not only here, but also in papers, so that then you can match them with people who will try to model these cases using like other tools.
Oh, yeah. Yeah.
Great.
Well, Phil, thank you so much, Steve. That was wonderful. Why don't we really kind of move into break mode? We have about 6 minutes left of break.